This video will show you how to calculate Martensite with intercritical annealing using the property model calculator and the steel model library in Thermo-Calc. The example requires a license for the steel model library and cannot be run with the free educational package. If you do not have a license, you can simply follow along with the video. The first part of this example demonstrates how to calculate Martensite fractions, which is the total Martensite percentage of an iron chromium carbon alloy that was intercritically annealed at two different temperatures. The Martensite fraction is calculated as a function of the temperature the alloy is quenched to, which in this case is 0 to 480 degrees Fahrenheit. The two temperatures that the alloy is annealed and quenched from are 1900 degrees Fahrenheit and 1550 degrees Fahrenheit. The example goes on to show how to calculate how the chromium content in the alloy influences the Martensite start temperature and 90% transformation temperature, or M90, after intercritical annealing. This type of calculation is useful for predicting how much austenite transforms to Martensite at different temperatures. In some cases, prior to Martensite formation, austenite coexists with some other phases, and it has a different composition from the alloy composition. Using the intercritical annealing option, you can run an equilibrium calculation at the intercritical annealing temperature, and the austenite composition can be automatically determined and used for Martensite calculations. The calculation is based on example PM-FE01 from the examples stored in your software. But in this video, I will show you how to set up the calculation, and I'll discuss the results. To begin the first calculation, open Thermo-Calc in the graphical mode, and select the Property Model Calculation template from the home screen. You may notice that there's a steel library template as well, but that is specific for TTT diagrams, so we will not use that. From the Databases drop-down menu, select the TCFE Steels and Fe Alloys database. You do not need the same version as I'm using, but you must have TCFE9 or newer to run this calculation. Next, select the elements iron, carbon, chromium, silicon, manganese, sulfur, and phosphorus. Next, we will define our system. So set carbon to 1.09, chromium to 1.52, silicon to 0.29, manganese to 0.32, sulfur to 0.018, and phosphorus to 0.005. This automatically sets iron to 96.757 mass percent. We will now set up our calculation, so select the Property Model Calculator 1 node. Select the Martensite Fractions model from the Steel Models group. If you click on the Description tab, you can read a brief description of the Martensite Fractions model, learn about some of the default values the program offers, and get suggestions for how to set up a calculation. From the top of the configuration window, we will leave the composition unit as mass percent, but we will change the temperature unit to Fahrenheit. We will set the temperature later as part of the one-axis calculation, so we can leave it as 1000 here. Notice that our composition carried down from the system definer, so we'll leave it as it is. Next, select the Configuration tab. Since this calculation involves intercritical annealing, change that option to Yes. Set the temperature of the intercritical annealing to 1900 degrees. We will accept the default for the other two fields. Remember, the Description tab provides information about why these defaults are set as they are, so you can read that if you'd like to learn more. Next, select the one-axis calculation type. Under Grid Definitions, leave the quantity as temperature and set the range from 0 to 480 degrees with 50 steps. Our calculation is now set, but before we run it, we want to set up an identical calculation with intercritical annealing at 1550 degrees Fahrenheit so that we can compare the two. First, we will rename this calculator node to avoid confusion. Right-click on the Property Model Calculator 1 node, select Rename, and name it Annealed at 1900 Fahrenheit. Then click OK. Now right-click on the node you just renamed and select Clone. This will give us an identical calculator. Right-click on this new calculator and select Rename. Change the name to Annealed at 1550 Fahrenheit and select OK. We want this calculation to be the same except for the temperature at which intercritical annealing will occur, so change that to 1550. Finally, we want to link this calculation to the plot renderer so that both calculations appear in the same plot. Right-click on the Plot Renderer 1 node, select Add Predecessor, and select Annealed at 1550 Fahrenheit. The plot renderer is now linked to both calculators. We'll accept the default values for the plot renderer, so our calculations are now ready to run. Right-click on the Plot Renderer 1 node and select Perform Now. Once the calculation is complete, a plot will appear in the results pane. This plot shows the total Martensite percentage as a function of temperature for an iron-chromium-carbon alloy that was annealed at 2 temperatures. The red line represents intercritical annealing at 1900 degrees Fahrenheit, and the blue line represents intercritical annealing at 1550 degrees Fahrenheit. We can see that the alloy exhibits a Martensite start temperature during cooling, and more Martensite forms as the temperature decreases. However, intercritical annealing at 1550 degrees Fahrenheit leads to a higher Martensite start temperature, and also higher Martensite fractions than the 1990 degrees Fahrenheit annealing. Therefore, we can say that the alloy annealed at 1550 degrees Fahrenheit has a lower austenite stability. If you run the example file that is included in your software, you will also see the experimental data, which has fairly good agreement with the calculated results. We will now set up the second calculation, which is to calculate the Martensite start temperature and the 90% transformation temperature, or M90, as a function of chromium. We will use the same system, so right-click on the System Definer 1 node, select Create New Successor, then Property Model Calculator. Right-click on the new calculator and select Rename. Name the calculator Chromium Influence, then select OK. This time, we will be using the Martensite temperatures model, so select that. As with all property models, this one also includes a description of the model and information about the settings. From the top, we will again change the temperature unit to Fahrenheit. Under the Configuration tab, set the intercritical annealing to Yes. We will set the annealing temperature to 1550 degrees as an example. We will again accept the default values for the other parameters. Select one axis as the calculation type, then change the grid definitions quantity to mass % chromium, because we want to look at how chromium affects the MS and M90 temperatures. Set the range from 0 to 3 and the number of steps to 50. Finally, we need to add a plot renderer, so right-click on the Chromium Influence calculator and select Create New Successor, Plot Renderer. Set the plot to Flexible mode, which will allow us to plot both the Martensite start temperature and the M90 temperature in the same plot. We will leave the x-axis as composition of chromium, since that is what we are looking for. Make sure that the y-axis is set to MS for Martensite start temperature. Change the temperature unit to Fahrenheit. Next, click the green plus sign and add another set of axes. We will leave the x-axis as it is, but we will change the y-axis to M90, and again, we will change the temperature unit to Fahrenheit. Our calculation is now set, so select Perform at the bottom center of the program. In this plot, the Martensite start temperature is represented by the blue line, and the M90 temperature, or 90% transformation temperature, is represented by the red line. Because intercritical annealing is applied, the changes of Martensite start and M90 temperatures are a result of equilibrium austenite composition at 1550 degrees Fahrenheit, changing with the system chromium content. We hope you enjoyed this video. If you have suggestions for videos you would like us to make, please leave us a comment. We're always working on new videos and would love to get your input. You can watch more of our videos at thermocalc.com in the video tutorials section.